Hi guys, Mr. Hedrick here in what will be our last video for this unit, wrapping up our discussion of exponential functions and logarithmic. We talked about exponential functions in past videos and how to interpret their key features, graph them, make tables of them, and transform them. We did a bit of the same in our last video. We saw that they are opposites of exponents. Logarithms have vertical asymptotes, for instance, whereas exponents have horizontal asymptotes. They do transform in the same way, but because they're opposites, like addition and subtraction are opposites, we saw that we can switch equations from one form to the other, that they'll have opposite types of key features. Domain and range will end up being something that's opposite as well, as we'll see a bit more today as we go through things. But where I want to start first is by looking at how to create a table of values for a logarithm. So there's two things that you can do. One of which is you can use an online calculator that is not Desmos related, so I'm going to recommend a website here at rapidtables.com. They have a pretty decent online logarithmic calculator that you can use as you're going through and trying to create tables of values. Or what you can do, if you want to keep using Desmos and their calculator, you can use your switching formula that we talked about in our last class. And these are two different methods that you can take to try to create a table of coordinate points x comma y that should match a graph that we will then be able to create by connecting our dots. Now, you can, or you should, be able to graph in Desmos as normal. But if we wanted to find a table not through graphing, if we wanted to instead start with a table and get to a graph, rather than use a graph to create a table, here's what we would have to do. I have an example of a function here, 2 times log base 2 of x minus 1, and we're going to try a couple of different types of each of these values for both methods. Okay? So for the online calculator, what you'll need to do, since you're not switching or doing anything like that, is simplify the logarithm first. Okay. So I have a base 2, and you'll type in something for x, like, I don't know, -1, for instance. And then into the calculator, you'll put this. Okay. Now what it's going to do, and notice I didn't include that +2 on the outside that you're multiplying by. The log calculator, right, this down here, only is able to calculate the logarithm, not anything outside like that multiplying by 2. We will have to do that later, that's okay. If we do try to calculate this though, it ends up being undefined. In fact, if you try 0 as a value here as well, it will be undefined, or +1. Okay. Error is another way to express this, and the reason that's the case, remember back to our discussion in our last video, we have a vertical asymptote here, right? What turns this parentheses into 0? We have a vertical asymptote at x equals +1. 1 minus 1 would be 0. We're going to have a vertical asymptote here. And it turns out the graph will not exist on the left side of this asymptote, nor will it exist on top of this dotted line, this asymptote here as well. Now the graph for the logarithm will exist everywhere to the right side of the page, but it's not going to exist anywhere to the left side, so x can't be -1. X cannot be 0. There's not going to be a y-intercept here, for example. Okay. So let's try a different number like +2. If x is +2, right, 2 minus 1 is 1. And if you take log base 2 of 1, that actually ends up being, I believe that's 0. And 0 times 2, because don't forget we do need to multiply by 2. 0 times 2 though is just 0. In other words, 2 comma 0. This is going to be a coordinate point for our logarithmic function. One coordinate point. Okay? If we type in 3, okay, 3 minus 1 is 2. Again, if we use the online calculator here, Log base 2 of 2 is going to be a 1. And 1 times that 2, don't forget, you've only calculated this section. 1 times this 2 is going to be 2. So 3 comma 2 will be another coordinate point. Okay. Hope you're seeing the pattern here. We're taking a number for x, right? Choosing a number like 4, plugging it in, simplifying the inside of the parentheses a little bit, get a 3, use the calculator. Okay, in this case, I believe that's going to be something like 1.59. You can verify that yourself. And that times 2, what's going to roughly turn out to be is 3.17. This is yet another coordinate point for our graph. So 4 comma 3.17 be roughly here. And now we can start connecting some dots, creating a table. Looks something like that. Okay, it's going to go up forever, down forever, right forever, but not to the left side forever, right? It's been cut off by our vertical asymptote we can find from that x value inside of our parentheses, x equals 1. So that would be the method that you would take for if you're going to use an online calculator. Now, you can do the same thing with a different method. Okay? Your switching formula. So in this case, what you'll need to do is rewrite this problem. You're going to change this into an exponential function. So I'm going to rewrite this up here. Use my blue marker. I'm going to rewrite that as y equals 2 times log base 2 of this parentheses. And the goal here is going to be to get x by itself. So we're going to see how that happens. First of all, I want to get the logarithm by itself. So divide by 2, get rid of anything outside your logarithm. Then use your switching formula. Remember this important thing that we saw in our last video? The base stays the same, everything else switches sides. So 2 is the base, 2 will stay the base on the right side of the equation, and everything else will switch. This fraction will move to the right side. That y divided by 2 will be an exponent. That parentheses, x minus 1 started on the right, will now move to the left. Okay. Everything besides this base has switched sides. And lastly, to get x by itself, we're going to add 1 to both sides of our equation. And now we have something set up where we can plug a number into y and get a number back for x using our Desmos calculator. Desmos is okay with you using exponents, exponential functions, and simplifying them, as long as you're using parentheses around that exponent. I mentioned that a couple of videos ago. Okay, so if we do that, what's going to happen if I plug maybe 0 into y, for example? If y equals 0, this is just an example, you can plug any number into y here. 0 divided by 2 is 0, right? Anything divided from a 0 is a 0. 2 to the power of 0 is 1. Anything to the power of 0 is 1, and 1 plus 1 equals 2. When y equals 0, x will equal 2. 2 comma 0, both methods, calculator method or your switching method, get you the same coordinate point. Okay, so I can create a table of coordinate points. You can plug some more numbers into y. For example, if you plug in the number 2 into y up here and simplify, it will give you back a 3 for x. Okay, and that's going to line up very nicely with your vertical asymptote, the domain and range, as we'll see in a second as well. Everything should fit. Your table should match your graph, should match your function, should match your key features, should match whatever calculator method you're using to simplify. Okay, so that's tables and graphs. What I want to do now is wrap up our discussion of logarithms and this unit actually with a final discussion of our remaining key features to talk about. So domain and range is one of them I wanted to highlight. Intercepts you can just get from a graph, so not as important. But domain and range are important because, remember, we're talking about something opposite of exponents. So when we talked about exponents and exponential functions in a couple videos ago, we mentioned that the domain is always all real numbers, right? The graph will show up left to right forever. And then your range will be a little bit more restricted. For logarithms, that switches. For logarithms, the range is always negative to positive infinity. Go back to our graph that we just created. The graph shows up everywhere up and down here, right? The range is up and down forever, negative to positive infinity. The domain, however, is restricted. The graph does not show up on the left side of the page. Domain refers to where does the graph show up? Left to right. It doesn't show up everywhere. It shows up everywhere after 1. So the domain here, for example, would be 1 to positive infinity. Okay. But it's not always the case that you have negative to positive infinity for domain. For logarithms, that never happens. The range is that. Okay, so another example here, for instance, identify your vertical asymptote. That's going to tell you your domain. Your range, again, up and down forever. For logarithms, it's the opposite of exponents. Okay, this graph goes down forever one way, up forever the other way. But we have a vertical asymptote here, visually speaking, at x equals negative 2. Okay. The graph might get close to that dotted line vertically, but it's never actually going to reach it. So our domain will be negative 2, and the arrow points towards the right side of the page forever, towards positive numbers, 1, 2, 3, forever towards positive infinity, from that asymptote, from negative 2. So the domain for logarithms is restricted, the range is not. Okay. And lastly, end behavior. Okay. Now, if you know your domain and range for a problem, that's actually very useful because that's always going to line up with your end behaviors, both for exponential and for logarithmic functions. We'll see that in a second. But just to give you a sort of understanding of what to expect in general, remember that your graph is going to head up and down forever. So you're going to have arrows pointing up towards positive infinity, down towards negative infinity. That will reflect your end behaviors for f of x. Okay. F of x will approach both positive infinity and f of x will approach negative infinity, but they won't approach it at the same time, right? One arrow will do that, one arrow will point up, the other arrow will point down. The question is, which one? Is it going to be the right arrow that points up, or is it going to be the left arrow that points up and the other one pointing down? That's the question. Okay, it all depends on your graph. It all depends on where the graph approaches the vertical asymptote. Logarithms always have vertical asymptotes. You'll have a dotted line somewhere. The question is, where will the arrows point? One will point towards the asymptote. The other will point either towards the left side of the page or the right, towards an infinity symbol. So either positive or negative infinity. One of the two, not both. Okay, the other arrow once again points towards the asymptote. Maybe it's better to just take a look at a final example here, okay, of a graph that we have given to us for the following function that you can graph in Desmos yourself if you're so inclined. This is the natural log. Remember, this is like a special logarithm that matches e to the power of something for exponents. I did go ahead and give you guys the intercepts here, right? X-intercept and y-intercept. Oh, these are switched actually. Whoops. Okay. X comma y, 0 comma 0.61, and then x comma y. Be careful. Always put those correctly. Okay. So the y and the x-intercept you can just find from graphing your problem. I'm not going to go into that too much. Or you can find it from your table of values. The asymptote here, in this case, 1, 2, 3, 4 units to the right, we have a vertical dotted line that we can create. X equals negative 4. This also makes sense, by the way, because -4 plus 4 will turn this parentheses into 0. Vertical asymptote, not horizontal. Right, this dotted line crosses the x-axis, this barrier. It prevents your graph from going any further to the left. So logarithms point up and down forever. The range is always the same. The domain, however, from left to right does not exist everywhere. It does not exist anywhere on top of or to the left of that dotted line, that asymptote. So it is restricted here to -4, all the way to the right side of the page forever. It does point that direction forever. Okay, restricted domain there. And now we can discuss end behavior, right? With an actual example, we can see the domain, these two values, -4 and positive infinity, they're going to go in these two blanks. Right? What does this mean? It means one arrow points towards the right side of the page forever, and it does, right? The other arrow points towards the left side of the page, but it doesn't go on forever. It stops or approaches -4 along the x-axis, right? -4. So these two blanks are going to get filled in by your domain. The only thing you're going to have to do now is figure out, for the range, do I put -infinity here or here? Do I put positive infinity here or here? Your domain and your range always fill in the blanks for your end behaviors. Okay, so what happens as I go towards -4, towards the left? Does my graph go up or down? Positive infinity in this case. Okay, that matches your range, that makes sense. The other arrow, as we go towards the right side of the page, right, this would be like left versus right. Okay, this would be up, and this would be down. This arrow goes downwards forever to match our range. It heads towards -infinity. Off to the side, keeps going down and down and down forever. So those are all your key features that you're expected to know for logarithms. They're the opposite of the ones that you expect for exponents, so keep those in mind, right? I have a good Desmos activity that you can check out on the activity feed of my eClass page there. It shows the difference in our last slide between exponents and logarithms. They're opposites in domain, in range, in asymptotes. One of the graphs will always have a x-intercept, logarithms always have an x-intercept, but not always a y-intercept. Okay? Exponential functions always have a y-intercept, but not always an x-intercept. So maybe that's useful to take a look at. I hope this video helped as well, and that does wrap up our unit on exponents and logarithms. And I hope this helped. Hope to prepare you for what you need, and always come to me with any questions.